Well, hello 3C, and this video is about exponential growth as well. We're going to call it exponential growth 2, and I'm going to get my little thing, exponential growth 2. Okay, this is the same goal as yesterday, just slightly different problems, just a little bit more complicated. So our goal, I can create equations for exponential growth situations. We're going to go over this general form one more time. This y here is the current value of whatever, oh, this isn't working. Hello. Pause. And we're back. And hopefully this will work this time. This gives us the current value. The A down here is the starting value. This B here is our growth factor. And the little x, the exponent, is the number of times that this growth factor comes into play, which we call the number of time periods. So let's have a look. We're going to do an example. Where finding the x value, the number of times something grows, is a little more complicated. Now this one in particular is very similar to the one we did yesterday. It's the next one that's a little more complicated. So let's take a look at example 1. In 1998, there were 96 children born in Mitchell. If the number of births since 1998 grows at a rate of 2.1%, determine the following. An equation to represent this situation. So here's the first thing we're going to do. First of all, this as a decimal is 0.021. Now if you don't know that, you take this number and divide it by 100, and that gives you it as the decimal point. And to divide by 100, we just have to put this back 2 spaces, and of course by putting it back 2 spaces I gotta stick this 0 in here as a placeholder. So now we're going to take a look at an equation to represent this situation. Y equals a b to the x. Okay, so we were told that the y is what we're trying to find. So here's children born, so let's call that b for births. A is the starting value, and the starting value, it started in 1998 with 96 children was the beginning of this thing, so our starting value is 96. Now what is our B? Well, since we're given this as a percent, our B is given by 1 plus the percent that we're given, 0.021. That's how we get a growth rate. We do 1 because it retains 100% of its value. This is telling us that there are at least 96 children born next year, and then there's 2.1% on top of that. So here's our growth factor, 1.021. That 1 represents 100% of the 96 and then a little bit more. And now the 0 here, we're going to let that be n, which is the number of years since 1998. Okay, so here's our situation. B equals 96 times 1.021 to the n. Okay. The number of children that will be born in Mitchell in 2050. How do we figure that out? Well, we're looking for the number of children born. So we're looking for this B equals 96 times 1.021, which means that I must have something I can fill in for that n. Well, n is the number of times this thing has been growing. So the growth rate is given as 2.1%, and unless it says otherwise, that's 2.1% yearly, and it's been growing since 1998 to 2050. So if you want to take the 2050 and subtract the 1998, and you will know that it has been growing for 52 years. Now that is what our equation needs, that 52 up there for the exponent, which is the number of years it's been growing. Now let's type this in. Where's my calculator? 1.021 to the exponent, that's this button here, 52. Now that's not a huge number, that's just 2.9 or almost 3. So that means that this has almost tripled since 1998. But I'm going to times it by 96 to get the exact value. Times 96 equals 282.8 or 283. We're not going to put in our little decimal point of a baby. So 283 births in 2050. Okay. So there, we've handled that one. Now let's go to the next one. Miss Sinclair was growing a bacterial culture with her grade 11 biology students. The culture started with 450 individual bacterium and doubles every 3 hours. Now that double is important here, but so is that every 3 hours. Now, the doubles tells us something about our B. In fact, it actually tells us our B. Remember when I said be on the lookout for those kind of things yesterday? Words like doubles, triples, by a factor of 5. So this one, the bacteria culture doubles, and that means that we're actually timesing by 2 every time. So we have a base of 2. Now this every 3 hours tells us something about how often it happens. So let's determine the equation in this situation. So let's write out the general form. Y equals a x to the exponent, not x, that should be b. Oopsie daisy. B to the exponent x. Now, in this case, we're talking about bacteria, or the population of bacteria. So I'm going to use P to stand for the population of bacteria. A is the thing we start with, which is 450. And now we have to figure out what we're multiplying it by. Well, we already figured that out, times 2. So our base is 2. So we times it by 2 for 3 hours. And then we would times it by 2 again after another 3 hours. And then we would times it by 2 again after another 3 hours. We don't know how many times we're going to do that, so I'm going to let n be the number of doubling times. The number of times it doubles. And now we're going to have to use that for the next one. It says how many bacteria will be present after 4 days. So if it doubles every 3 hours and we want to go every 4 days, here's how we're going to figure it out. In one day there are 24 hours. 24 hours per day. If it doubles every 3 hours, how many times does it double in one day? Well, let's do divide by 3, and that means it doubles 8 times every day. Now, after 4 days, we will have to do 8 times 4, which is 32. So it doubles 32 times. So we have to do this little calculation before we can plug right into here. And now this is how many times it doubles, which is we have to sub back up there in the end. So P equals 450 doubles 32 times. Now I have a sneaking suspicion this number is going to be big because 2 to the 32, that's a lot of bacteria. So let's pull out my handy calculator. It's got that number from the last one. We'll get rid of it. 2 to the exponent 32. That's pretty big, and now I have to multiply it by 450 times 450. Now, my calculator has not kicked into scientific notation, so I can write this whole thing out. Your calculator might kick into scientific notation. I'm going to write this out. I'm going to move my calculator so I can actually see it while I write it out. And that is 19327352833200. That's a really big number. Now your calculator probably did this to you. It probably did 1.9 and then gave a little e or a little space or a little times 10 to the, and let's see how many places it's going to give us. It is here and we need to move it over to there. So it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. It's times 10 to the 12 is what that will have given most calculators. And that is a lot of bacteria. And that is the end, as soon as I write this word, bacterium, or bacteria, we're going to call that quits. That's the end of the video.